Today, in this video lecture, we will see Chapter 3 Torsion on Strength of Material subject. So, introduction. A member which is subjected to the couple which produce rotation about its longitudinal axis is known as twisting moment or torsion. Member subjected to couple and this couple produce rotation about its longitudinal axis is known as twisting moment or torsion. So, consider this member as a circular shaft. This dotted axis is longitudinal axis for this shaft, and this is x-axis. Consider this longitudinal axis as x-axis and vertical axis as y-axis. And perpendicular to this longitudinal axis is this z-axis, transverse direction z-axis. And this couple is like this. Here say this rotation. This couple produces rotation about its longitudinal axis. Rotation about this x-axis. This couple produces rotation about this x-axis is known as twisting moment or torsion. Second point is, due to torque applied on shaft, the shaft produces shear stress and shear strain in the material. Shaft produces shear stress and shear strain in the material. In our first chapter of strength of material subject, we learn shear stress and shear strain. Shear stress is nothing but here shear stress. Shear stress is nothing but when two equal and opposite parallel forces acting tangential to the surface of the body is called as shear stress. That means, consider this as a body acting parallel and opposite forces to the surface of the body. When two equal and opposite parallel forces acting tangential to the surface of the body is called as shear stress. And second term is shear strain. Just for example purpose, I show this diagram. Shear strain is the measure of the small distortion of the block caused by the shear force is called as shear strain. Shear strain is due to the shear stress, the measure of the small distortion of the block caused by the shear force. Due to shear force, there is distortion, small distortion or small deformation occur in this block, and this is known as shear strain. Consider this as a point, and when we apply shear stress here, this circular shaft twist and this A comes to A dash. This angle and the measure of the small distortion, that means this angle theta, the measure of the small distortion of the block caused by the shear force is called as shear strain. And due to torque applied on the shaft, this shaft produces shear stress and shear strain in the material. Third point is, in practice, torque are produced in shaft of motors or power equipment, example fans, axles of vehicles, pump, etc. Shafts are circular in section only. Hollow shafts are preferable for design. Second, twisting moment or torque. when a force is applied tangentially to a cylindrical rod at a certain radius in the plane of its transverse cross section, the rod is said to be subjected to twisting moment or torque. It is also defined as tangential force and the radius. So consider this as a cylindrical section of a cylindrical rod. This is circular section, and when a force is applied tangentially to the cylindrical rod, consider force as F acting tangentially to the cylindrical rod at a certain radius in the plane of its transverse cross section. Yes, this F is as a transverse cross section. That means this is x-axis, this vertical is y-axis, and this z perpendicular to this x-axis is transverse axis, and this F acts like this. And we take cross section here. The rod is to be subjected to twisting moment or torque. It is also defined as tangential force and the radius. So this is one terminology in this torsion concept, twisting moment or torque. Now next we see assumptions made in the theory of torsion. First assumption in the theory of torsion is the shaft should be perfectly straight and uniform in cross section. This shaft is straight. See, shaft should not be bent or curved type. It should be straight and uniform in cross section. Cross section similar at any distance from this. Next assumption made in the theory of torsion is material of shaft is homogeneous and isotropic. So this homogeneous means property of this material is same at every point. Somewhere here, at any point property same. That means homogeneous. Homogeneous means property same at any point. And isotropic means property same at any direction. Is x direction, y direction, or z direction. Third point is circular shaft remains circular after twisting. So after twisting, somewhere here, twisting, here, twisting. After twisting, and this is x-axis section, this is x-axis section. After twisting, this shaft change from this point A point to A dash, but it remains circular. This is third point. Fourth point is plane section of shaft remain plane before and after twisting. This plane section of shaft remain plane. This section should not be bent or any other shape. Twist is uniform along the length of the shaft. This twist is uniform same throughout the length of the shaft. That means somewhere here twist is same, here twist is same. Maximum shear stress induced in the shaft does not exceed the elastic limit. See, this point assumption is important. Maximum shear stress is within elastic limit. So when we remove this maximum shear stress, material comes to its original position. And last point is torque applied on the shaft in the plane of perpendicular in the axis of the shaft. This x is the longitudinal axis of the shaft, and this torque applied on the shaft in the plane perpendicular to the axis of the shaft. So this is the axis of the shaft and torque applied perpendicular to it, like this. Torsional formula is T upon J is equal to G theta upon L is equal to tau upon R. T is nothing but the twisting moment, J is polar moment of inertia, G is modulus of rigidity, theta is angle of twist in radian, R is radius of shaft, and this L is length of shaft, and this tau is shear stress. This tau shear stress. So twisting moment we all know T, theta angle of twist in radian. Angle of twist in radian is this. This is T, twisting moment. Due to this twisting moment, this A point here is shift toward this A dash. Between this A and A dash is angle of twist theta. And this R is radius of shaft. R is this radius of this shaft. L is length of shaft. L is this. Tau is shear stress. Here, polar moment of inertia. So, in next slide, we will see what is polar moment of inertia. Polar moment of inertia and modulus of rigidity. Modulus of rigidity, we already see in our chapter 1, stress and strains. Once again, we see it, modulus of rigidity. Or we also call this modulus of rigidity as shear modulus. Modulus of rigidity is the ratio of shear stress and the shear strain is called as modulus of rigidity. And this modulus of rigidity is denoted as capital G. Capital G is equal to shear stress is denoted as tau and shear strain is denoted as phi. This is modulus of rigidity or shear modulus. The ratio of shear stress and the shear strain is called as modulus of rigidity. Next concept is polar moment of inertia. This polar moment of inertia is the moment of inertia of a plane area with respect to an axis perpendicular to the plane of the figure is called as polar moment of inertia. First see definition. This polar moment of inertia denoted as J or IB. It is denoted as J. The moment of inertia of a plane area plane area with respect to an axis perpendicular to the plane of the figure is called as polar moment of inertia. Polar moment of inertia denoted as capital J, the moment of inertia of a plane area with respect to an axis perpendicular to the plane of the figure is called as polar moment of inertia. Let us consider this body and moment of inertia of this body. This is x-axis and this is y-axis. Perpendicular this z-axis to this body is polar moment of inertia. Let us consider this circular shaft. Cross section x-axis of this circular shaft is like this. Let us consider this as a x-axis and this as a y-axis, and perpendicular to this axis, that means let us assume this axis is z-axis. This z-axis is polar moment of inertia and it is denoted as J, and unit of this polar moment of inertia is mm raised to 4. So we see for solid shaft this polar moment of inertia, solid shaft, capital J is equal to Ixx plus Iyy. This Ixx Iyy similar for this circular section. So 2I and moment of inertia of this circular section is pi d raised to 4 by 64. So polar moment of inertia is for this circular section is pi by 32 d raised to 4. Next we will also see for hollow shaft this polar moment of inertia. Here this is solid shaft, circular solid shaft of diameter d, small d. Now for hollow solid shaft, let us consider this as capital D diameter. This is circle and small d diameter. This is hollow circular shaft. Polar moment of inertia is J is equal to Ixx plus Iyy. That means 2I for circular shaft. Moment of inertia about x-axis and y-y axis both are symmetrical. So J is equal to 2 multiplied by d raised to 4 minus small d raised to 4 upon 64. So polar moment of inertia is here pi value is, so pi d raised to 4 minus small d raised to 4 upon 32. This is polar moment of inertia. Capital J is equal to pi multiply by under bracket d raised to 4 minus small d raised to 4 bracket complete upon 32 for hollow shaft, and for circular shaft pi d raised to 4 upon 32. And modulus of rigidity is shear stress to the shear strain, denoted as capital G. This is torsion. Introduction. Twisting moment. Assumptions made in the theory of torsion. Torsional formula: capital T upon J is equal to G theta upon L is equal to tau upon R. T is twisting moment, J is polar moment of inertia, G is modulus of rigidity, theta is angle of twist in radian, R is radius of shaft, L is length of shaft, and tau is shear stress. T upon J is equal to G theta upon L is equal to tau upon R. So this is introduction to this torsion chapter, third chapter of strength of material subject. Thank you very much.